Hello friends, welcome to our channel. Let's look at a daily challenge problem that is 2071, maximum number of tasks you can assign. In this video, we're going to explain a solution based on binary search. So the binary search is on the number of tasks that can be assigned. So our plan will be for sure do binary search. We will use two steps. So one is to define a Boolean function. So the role of this Boolean function is to produce order or monotonicity. And also we need to do some thought to mimic the process of assigning tasks. So the second part will be search space shrinkage, right? So here I want to first specify some notations. So here W will be the work ID in my code, and T will be task ID in my code. So with that said, I'm going to directly go to the coding. We will not go through the problem statement. You can review that by yourself. But here I want you to have look at this constraint. First, the number of tasks and the workers might be different, but both of the two are bounded above by 5 times 10 to the power 4. So this is a decent large number. Therefore, we need to think of time complexities. And the number of pills is greater than or equal to 0. Can be 0, right? Or can be m, but at most m. Because if you have more than m, so you can just increase the worker's ability by this strength. Then you just consider assign the task. That will be a slightly easier problem, right? So also the tasks and workers' strengths are all non-negative, right? So with that said, we are going to do the work. So here, both the two parts, define the Boolean function and also search space shrinkage are non-trivial, right? Let me first do some thought, because this will basically follow this one. Is it possible to assign the first key easiest tasks to the workers, to the strongest workers? In other words, if the strongest workers can finish the key weakest task, then we can try for different keys, right? So for this, I'm going to do some thoughts. So first, tasks sort. So here is from, it's increasing, right? Order. And then I'm going to do workers sort. So here I'm going to do reverse, this is true, decreasing. So the logic is simple. I want to first try the easiest tasks, but among the easiest tasks, I want to assign stronger worker with the relatively harder task, right? That will be the assign. So now I'm going to define the Boolean function. So the Boolean function is that if we can finish or assign key tasks. So as we write like this, for sure we need to think of easier task, the key easiest one. That's why we sort from increasing and pick the first key. Here, let me write this function. We can assign the key. So here I'm going to, as I mentioned, I'm going to use W as the worker ID. So I'm going to try the first worker first. So the worker ID, or the worker ID that is not assigned yet. You can understand like this, right? So number of pills will be the pills, right? Because here in we need to call different number of times of this function. So we cannot alter this pills. We can introduce this here, and then we alter this in pills, right? So for the candidate, I'm going to I'm going to make a deck. So if you write a complete this collections deck. So then let's look at the assign. How do we assign this? So basically I'm going to iterate. This is for task ID, right? For in range k minus 1. So in other words, our target is to finish the first key task, but we still focus on the harder task using the strongest workers at the very beginning, right? So then for finish this task, what we need? So then this is a task T. So this is the strength we want to use. Then we are going to check if so basically the order is very important. First, I want to use this if not candidates. This is the one. We do not have a thing in the queue, and so the workers, the current worker ID, that's W, has a strength greater than or equal to need. So this means using the current strongest work, we can finish the strongest tasks inbound. So then we are going to increase the worker ID by 1. Then we try next worker. And this one, we just need to continue. We jump to the out of the loop and look at the next task. This is the one. So if it's not the case, in other words, this is not empty or this is less than the needs, then let's try another situation. Another situation is if candidates, and so the candidates, the first one, this is the strongest, because here in the queue I'm going to put things into the queue with strongest in the head, right? The head will be the left side of the deck, right? So if this is greater than or equal to need, then we can use the current worker. So we are going to do candidates pop left, right? And then it means that we finished the current task ID or task. So we continue. This is the one. If we still cannot finish the task, then we are going to consider this. So we queue. So W is less than K. We consider other workers and potential workers. That's why we write as candidates. We found the potential workers that can possibly finish the task. So if workers, the worker ID plus the strength is greater than or equal to the need. In other words, if we use a pill to boost that worker, it has the potential to finish this task. So what we are going to do is candidates append workers W, right? Then W is incremented by 1, right? What does it mean? After we exit this while loop, if the candidates is not empty, and it means that we can use pill to this, let's see, if candidates is not empty and we still have pills, right? Then we can give pill to candidates, any candidates in the in this queue, such that as long as they have a pill, they can finish the current task. For in this case, for sure, we want to use the weakest candidates, right? Therefore, we do candidates pop from the tail. This means that I'm using the weakest workers among the queue, but that is strong enough after we give him a boost to finish the current task. Then we continue, right? Also I forgot. So we need to decrement the pills by 1. This is crucial, right? If you have this candidate but you do not have pills, still we cannot finish the task. So if we cannot finish, if we check this, and check this, these 3 ifs, if we still cannot finish the current task, then it's impossible to finish this task. Therefore, it's impossible to finish the key task. So we're going to return false here, right? And then after this for loop, if nothing has returned, so we can return true. This will be the logic for a can assign. But here, before we do binary search, in other words, search range shrinkage, one want to notice that this sorting is important, right? And also, you need to know here the order. We first check if we can use the current worker without a potential boost, if it can finish the task, or if the current worker cannot, but we have some candidates, so with the some pill, so we can finish that. right? This is the without using the pill in the candidates. And then if this is not true, then if we want to check if in the candidates with a pill they can finish. If all those possibilities cannot finish the task, we just return false, and then finally we return true. So this will be our Boolean function. So next we are going to do search space shrinkage. So for this, actually, basically we translate this problem to be find the max key such that can assign key is true, right, or equals true, right? So this is our problem setting. So here for the search, how many tasks we can finish? So we have low, we have high. The lowest possible is 0, right? You can finish and nothing. And then the maximum, it will be the because one worker can assign at most one task. So therefore, this high will be the mean of the length of the tasks and the length of the workers, right? So once you have this, so here I'm going to initialize a result. If you can finish anything, can't finish anything, so the result will be 0. Then we're going to check, well, low is less than or equal to high. Then we can look at the middle. The middle we can compute like low plus high integer division by 2, or you can do half, high minus low over 2, right? And then I'm going to make a check, can assign. If we can finish at middle, right, then I'm going to update the result to be a larger one. And then I'm going to set the low to be mid +1. Then because I'm going to check again, right? Then otherwise, so if at mid you cannot finish, so it means that you should finish less than mid task. So we are going to set the high to be mid -1. So overall, we just need to return the result. So this will be the full search space shrinkage. So before we make any comments, let's first do a test. Runtime error. So what's the problem? Name candidates is not defined. It's in line 33. Let's see. Candidates. This should be better, I guess. Yeah, it passes the 3 test cases. So now let's look at the generic case. Yeah, it passes all the cases and it's decently fast. So here in this problem, so here you write low less than or equal to high is important, because here I'm writing low. So though in this case I use a result variable to retrieve the true one, because in this if check can assign applied to mid is true, therefore at least I can update the result to be mid. Then I choose low to be mid +1. So this way we can always break this condition and make it converge. So that's actually a point you need to notice. In some of the cases, you can write low strictly less than high, but here you write low to be mid, but without introducing this result variable, and finally you return low or high according to your needs. But here, this way of getting the return is actually a good strategy. So that's basically one comment you need to notice. Here I'm writing less than or equal to, and here I'm writing low, mid +1, right? So here is mid -1. Therefore, the reason is that I have already checked this one, assigned this result to be mid when we check is true. I don't need to check send it again. Therefore, I write different numbers, no matter low or high. So that's the one point for a high-level understanding. Basically, you need to, it's best you walk through this example or manually, so to digest the full detail. With that finished, let me share another comment. So here we have a YouTube channel which has a playlist called Binary Search. So you can actually check out those videos there and do some practice on different application use cases or different situations. I believe that will boost your understanding of binary search. With that said, that's it for the current video. Thank you for watching.